glad you're back for section 4.2. We're going to talk about binomial distributions. Maybe the first question you have is, what does binomial mean? Well, I checked on that. And it seems this word binomial does have a beginning to it. Bi means two, and nomial means parts. So we're going to talk about distributions that include two parts in it. We've already talked about the probability distributions in general, and what we're going to do now is we're going to get more specific and talk about binomial distributions, and in the next one we'll talk about a couple of other sort of interesting ones. I think you'll enjoy the trip. Okay, where am I? There we go. Those are some things we're going to do. And one thing you might want to remember is we are not going to use a table. We're going to use technology. Let's get the concepts down and let's make calculations when needed be done by the calculator. So here we go. What is a binomial experiment? We're going to use a fixed number of trials, 17, 52, 100, whatever, fixed number of trials. Each trial is independent of the other. In other words, when you do the first trial, it does not change the probability of the next trial. There are only two possible outcomes. That's why we call them binomial experiments. And although this is a little bit unusual at times, we're going to call one of those outcomes a success and one is a failure. It's not a judgment, it's just a choice, one over the other. That way you know what you're interested in and what you're collecting. The probability of the success, the same for each trial. Notice up here we said they're independent. That's part of this. The probability is the same for every trial. Also, the random variable x, the number we're going to be focusing on pretty much, is the number of successful trials. In other words, whatever we're interested in, x represents how many times we got that result. Here are the numbers you need to know, and you'll be using them in your calculator, for example. First of all, n is how many times you're going to do the trial. Remember, it was a fixed number of trials, and this is how many times you're going to do it. P is the probability of success in each of the trials, and they're all the same probability. Q, we're adding an extra one. Some books don't do that, but I prefer it because it makes some of the calculations or the equations a little bit simpler, but it's very simple. Q is just a complement of P. It's what's left over in the probability. If P doesn't happen, then that's Q. And X is how many times whatever it is we're interested in happens during the N trials. So those are the four numbers you're going to need. When you calculate most of these, you're going to need N, P, Q, which you can find by using P, and X, your focus. These are commas, by the way, not ones. First of all, let's get this down properly. Do you understand what a binomial experiment is? Well, let's give a couple examples here and see how you can do. Again, I suggest that as each of these examples or questions comes up, hit the pause, probably in the space on your calculator or computer rather, and try it yourself. See if you can get it right. If you can't, even by getting a wrong answer, you're going to learn. So please do that. So we've got a surgical procedure. We keep going back to that over and over. 85% chance of success. So you're hoping you're that 85% if you're having the procedure done. The doctor's going to perform the procedure on 8 patients. That would be n equals 8. This is p equals 0.85, which means q is 1 minus p, which in this case, 1 minus 0.85 is 0.15. And x is going to represent how many successful surgeries. So it's a binomial experiment because each surgery is like a trial or an experiment. Excuse using the word experiment, but it's just another way of saying the same thing really. 8 surgeries, that'd be n. Each one's independent, good. Only 2 possible outcomes, success or failure. Now this time, success and failure really are meaningful. And there's the probability of success, and 1 minus probability of success is the probability of failure, which we call Q, and this is P. And X is going to represent how many successful surgeries. So here we go. We're going to have 8 surgeries. Here's the chance of success on each one of those independent surgeries. Here's the probability that the surgery is not successful. And here are the X's or results that we might be interested in. This would be none of those surgeries were successful. This would be 1 is, 2 out of the 8, 5 out of the 8, or all 8. We'll get back to something similar to that, but that's just deciding whether it's a binomial experiment or not. So let's check this one. We've got a jar that's 5 red marbles, 9 blue, 6 green. You randomly select 3 marbles from the jar without replacement. The random variable represents the number of red marbles. Now, I'll give you a tip before you hit the pause button. If you're interested in the red marbles and you pull out a marble, each marble means either it's red or it's not. Just a little tip. But it's not a binomial experiment. The probability on the first trial is 5 over 20, okay? 5 red marbles, 20 marbles in all. But they're not replaced. So the next time, either the probability on the next one will be 5 over 19 because we haven't picked the red marble the first time, or it'll be 4 over 19 because we already took out a red marble and did not put it back. So the trials are not independent, and that means we do not have a binomial experiment. Wow, that's a lot. Actually, it's not quite as complicated as you might think it is. This is a combination thing. If you really wanted to do this, now You've already picked out X. You've already figured out what N is. So you've got all these numbers. If you really wanted to do this in your calculator, what you could do is you put the number N, like a 19 or whatever it is. Then you can go to the probability menu, get the combination, put your X number in, whatever that is, and then times, and since you've already got the probability, all you have to do is put this X that you figured out, and then Q, you take the N and the X that you have, and N minus X will be the exponent for the Q. Remember, Q, again, is just 1 minus P. However, we have an easier way of doing this. So remember what these things represent. N is number of trials, probability of success, probability of failure, the number of successes we are interested in those N trials. We are going to use the TI-84 to do this. And to get to binomial probabilities, you're going to, the second key on some of your calculators will be blue. It might be gold on some. And after hitting that, you'll hit the VARS key. Now that's going to get you to a menu. And this is a rather long menu. What you have to do is you have to go the whole way down to BINOM PDF. Binomial probability density function is what it represents. For you, what you're going to do is you're going to find the probability of a binomial distribution where there are N trials, P probability on each event, and you're interested in getting X results, X successes. And this will give it to you. Once you bring this up, put these three numbers in, hit enter, and you'll get the probability of a success X times. Remember, N is the number of trials, P is the probability of success, X is the number of successes in those N trials. Now you might notice that Q is really not here. Q, what's the deal here? Well, the deal is this. Your calculator is smart enough that it knows that Q is 1 minus P, so you don't need to put it in. Pretty nice, huh? All right, let's give this a try. We've got rotator cuff surgery, has 90% chance of success. So what actually, the way I would do it is I'd make a little box for myself and put these things in. I want N, I want P, you might or might not want Q, and we definitely need the X as well. You need this, you need this, oops, and you need this. You don't really need Q because the calculator is going to take care of that. So 90% chance of success. We'll put P equals 0.90. The surgery is performed on 3 patients. 3 patients, 3 trials. I'm going to do it 3 times. Find the probability of it being successful on exactly 2 patients. Now, the way we're going to start is by talking about exactly. When we have a different situation, we'll do something a slight bit different, but it'll be pretty easy. Now we want exactly 2 patients, so that's the grand total of successes that we're interested in. So what we're going to do is we're going to put a second VARS. Remember, we're going to pick out it's option A, PDF. Now make sure you don't go, there's another one called binomial CDF. But when we're talking about exactly a certain number of successes, we want to use PDF instead. So make sure you pick that one out. Once you do, you're going to put in these three numbers. The number of surgeries, the probability in each one, and the number of successes that you're interested in finding the probability for. Now you could do a diagram like this. And you might want to do this one time. You might not want to do it very often because I've just shown you the shortcut. But this gives you an idea of how your calculator sort of puts this together. And your probability, these are the three that have exactly 2 successes. You add those up or just multiply 3 times that 81 over 1,000. And there's your probability that if the surgeon has success on 90% of the surgeries and he performs 3 surgeries, this is the probability of getting exactly 2 successes that day. So you're going to use the TI-84. You probably are going to put in 0.9 here. You won't need this one. If you did, you'd put 0.10, but you really don't need that. And you will need the 2. There's a 3, there's a 0.9, there's a 2, and you don't have the Q at all. And there's our probability. Well, let's try another one. These can be fun, actually. Just relax, have fun. So I'm going to start as I usually do. I'm going to, on a scratch piece of paper or somewhere, I'm going to put the essential details. Remember, I'm looking for N, P, and X. So as I read through this, U.S. adults were asked how often do they go online. The results are shown in the figure. Okay, so we're talking about down here. 6 adults who participated in the study are selected. So 6 adults. And construct a binomial probability distribution for the number who respond. Okay, so we're doing something a little bit different. So we're going to actually need several of these. Now, how do we do that? Well, it says here, let's see, we want to construct the probability they go on several times a day. Several times a day. So right away, we want to go with this one because that's several times a day. So this be 0.48. Notice X doesn't appear here. That's because we want the probabilities for all of them. Well, what are the possibilities? You might want to make a list. How many successes could you have? Well, you're asking 6 adults. Maybe none of them say that they go on several times a day. Or 1, 2, 3, 4, 5, 6, 7? No, you only asked 6 people. So these are the possibilities. So what we're going to need is the probability that you got 0 people saying they used the internet or went online several times a day. And this one is the probability for 1. This needs the probability for 2, and so on. Each one of these, for example, I'll do 2 of these for the probability of getting a 0, you're going to use, binomial PDF. And the first one is n. We've got 6 people we asked. The probability for each one we got out of the table over here, 0.48. And for this first one, for the 0, we put a 0 there. That's not all of them. We have 7 different probabilities to get. So how about the probability that we get one person saying they get on several times a day? Again, go to second vars, binomial PDF. Sorry, it's a little bit messy. Still 6. Probability is the same. The only thing that's different is we're interested in one success. What is the probability of getting exactly 1? And you're going to do this 7 times. Once for 0, once for 1, 2, 3, 4, 5, and 6. And make a table out of that. So there are the results, except that you're going to use binomial PDF. For example, let's pick the probability of getting 4 people saying that. Well, you're asking 6 adults. The probability on each one is 0.48, and you're interested in getting 4 yeses, and that'll give you that result. You do that 7 times using 0, 1, 2, 3, 4, 5, and 6 in this location. Get familiar with going to second vars. Notice this represents the distribution menu. And you have to go way down to get binomial PDF, but you'll get familiar with that. In fact, I'll give you a hint. When I go to second vars, which is really distribution, what I do to get there a little bit faster is I cursor up, which gets me to the bottom of the list, and then binomial PDF is easier to pick out because it is way down there. It's about number 11 or 12. You can figure it out for yourself. So there are our possible values for the probabilities of 0, 1, 2, 3, 4, 5, and 6. There is our binomial probability distribution. Remember, these are the possible yeses for going occasionally online. We ask 6. You could get 0, 1, 2, 3, 4, 5, or 6. And we'll use the calculator to get these probabilities. Now you'll have to do it 7 times. There is no shortcut there. Notice also, we've learned in the past that for a probability distribution, we talked about this last time, we should get a 1 there. Why isn't it a 1? Well, the reason is because all of these are rounded. Oops. And because they're rounded, sometimes they're rounded up, sometimes they're rounded down, and so these are really good approximations, but they're not perfect. So when we add them up, sometimes we get very, very close to 1. It should be very, very close to 1. If it's far off, if the sum of your probabilities is something like 0.87, there's probably a problem there. You need to go back and do it again. All right, let's try this on an example. Survey found that 75% of US adults are experiencing digital device fatigue. Wow. All right. I want to make sure I don't lose that. I don't want to read this paragraph over and over and over 10 or 16 times. So the 75% is going to be my probability, 0.75. Change that percent to a decimal so you can put it in your calculator. And you randomly select 100 adults. That means 100 trials. So n equals 100. What's the probability exactly, and that's all we're doing right now, exactly 66 experience fatigue. So x is 66. Now you can do it the long way if you want to, but I'm not going to. That's why I have a suggestion. Use technology to find the probability. Since it says exactly, we're going to go to second, vars, and that gets us to the distribution menu. We're going to go all the way down until we see binomial PDF still. And n goes first. That's 100. We put that up here so we can easily see it. We don't have to read through this whole thing and find out what n is. Next goes the probability, 0.75. And then which result are we interested in? Getting exactly 66. And there are different ways of doing it. You could do it in Excel if you wanted to, and this gives you an idea of what you'd have to type into one of the cells, and that would give you the answer. But we'll use the TI-84 Plus because that's what most of us have. You could use Minitab. I actually taught that one time. You could use Excel because most of you have it on your computer anyway, and most of us wouldn't have StatCrunch, although in some classes they actually do use StatCrunch. So there's a handful of ways you can do it. We're going to stick with this one. So you can see that the probability of getting exactly 66 adults when you choose 100 to survey is this decimal, 0.01116782235. And our little reminder, would it be unusual? Well, if it's less than 0.05, alias 5%, it's unusual. This is definitely less than 0.05, so it's an unusual event, getting 66 adults. Let's try this on another one. So this survey found that 22% say that economy, unemployment, and jobs are the most important problems facing the U.S. today. So I'm going to start with my box. 22% represents the probability, so I'm going to put that down in my box so I can see it easily. You randomly select 4 adults. That would be n. So n equals 4. And what are we interested in? We want the probability exactly to respond yes. So the x is going to be 2. And we'll get back to 2 and 3 in a moment. So how do we get that? We'll go to second vars. So you're going to need binomial, PDF because we're talking about exactly 2. Put the numbers in. You pick 4. The probability is 0.22. And you're interested in getting exactly 2. And I would suggest you do it on your calculator right now. Why not? In the meantime, come back in a second and we'll work on the other two. The other two are more interesting in a way. Well, this is part one, and we'll use this to get the answer for that one. Let's take part two over here. Now we're doing basically the same thing, but what are we interested in this time? This time we're interested in at least two. At least two. Okay, we're going to do this a little bit differently. First of all, we're going to make a list of the possibilities. Well, if we selected 4 adults, how many of them are likely to say that those are the most important problems? Well, it might be 0 out of the 4, or 1, or 2, or 3, or 4. It can't be 5 because we only asked 4 of them. Now, what are we interested in? It says at least 2. So what we're interested in this part of the problem is a 2, a 3, or a 4. Those are at least 2. Now, how do I get that? Well, there are a couple of ways of doing that. One way would be by taking the binomial PDF and getting the probability for 2. So it'd be 4, 0.222, plus, you need to add in 3, so you add binomial PDF, sorry, a little sloppy here, 4, 0.22, and we want 3 this time, plus binomial PDF, 4 trials, probability of 0.22 and 4. Add those 3 up, and that's easy to do in your calculator. You can put them in like this actually. Put the first one in, put a plus, then go back and pick up the second one, then the third one, and that'll give you your result. However, there's a clever way of doing this faster, especially now here there are only 5 different possibilities, but if there's 17 or 50, you wouldn't want to be doing all this to 50 different possibilities, would you? Well, let's take this relatively easy one because you could do it both ways, and let's do it the way that would be simpler if these were much more. So you've already seen that below binomial PDF there's a binomial CDF. Okay, what does that mean? Well, of course they're connected. This one means binomial cumulative distribution function. The thing to remember with this one is when your calculator adds these things together, it always starts with 0, gets that probability, goes to 1, gets that probability, 2 gets that probability, up to a certain point. Actually, you call that X. The catch is we can't tell it to start at 2 because it always starts with 0. But being the clever people we are, we know that 2, 3, and 4 is the complement of 0 and 1. The probabilities of all of these together add up to 1. So what we can do is, to get the probability of 2, 3, or 4, we'll take 1 minus the probability that we get a 0 or 1. And because our calculator with binomial CDF can do this, that's how we're going to do it. So on our calculator, we'll take 1 minus. What don't we want up here? We don't want the 0 and the 1. So we're going to subtract that. So we're going to get binomial CDF. And we're using 4 different adults. The probability on each one is 0.22. And what we want the calculator to do is keep adding the probabilities until it gets to the 1. It'll calculate this, you'll subtract it from 1, and what you'll end up with is the probability of getting a 2, a 3, or a 4. You got that? If necessary, go back and go through it again. All you have to do is rewind a little bit and go over the question again, try it again. All right, so that is how you would do part 2. By using the complement idea. Now, number 3. For this one, we want fewer than 2. Fewer than 2. Let's make our list. What are our possibilities? We've got it up there in the upper right. As if we were starting from scratch. We asked 4 people, so we could get 0 results. 1, 2, 3, or 4. This time we want fewer than 2. So this time we're interested in those 2. Notice that these probabilities start at the bottom at 0 and go up to 1. So that's exactly how binomial CDF works. So all we need to do is go to second, bars, which gets us to the distribution menu. And we're going to pick out binomial CDF. And we're going to put the numbers in we need. We're going to have 4 trials. Each trial has a probability of 22%. And we're going to have the calculator add the probabilities until it gets to 1. No more. Just 0 and 1. That's less or fewer than 2. So stop calculator, stop when you get to that 1. And that'll give you the result. So let's take a look at this. For part 1, it was exactly 2. That's why we use binomial PDF. There's the number of trials, the probability, and exactly 2. And there's our probability. Try it on your calculator. Get familiar with going various places on your calculator. Try it yourself. Make sure this is exactly what you see on the screen. For the second part, remember one way of doing it was, since we're interested in 2, 3, or 4, we're going to add those up. So we get these 3, and we're going to add those together. Add those 3, and here's the probability that you get at least 2. In other words, about 21%. And there's the shortcut I showed you. And this shows you what you're doing is you're getting a complement because you're subtracting the ones you don't want from those in the grand total, which is always 1. Next, you want the probability of fewer than 2 adults. I really don't think you want to do it this way, do you? I don't either. And we won't be doing that. This is your X. This is your n minus x, and so on. To get it in one step, your calculator is going to start at 0, add the probabilities until you tell it where to stop. In this case, stop at 1 because we don't want 2 included. Only the 0 and the 1. Don't go beyond that. Because we want fewer than 2. And there's your answer for the third part. All right, let's try another one. We've gone through that pretty exhaustively, I think. So 5% of the workers, I'm going to start right away. So I have a probability of 0.05 commute to their jobs by using public transportation, not counting taxi cabs. You randomly select 8 workers, so there's our 5%. That's the probability. 8, that's our n. So put that over here with the rest. What's the probability exactly 3 use public transportation? So we're going to pick 8 workers, and we want to know what's the probability of getting exactly 3. Exactly means, here we go, exactly means you're going to use the PDF function. Exactly means use PDF. So you're going to go to the second bars, and you're going to go down to binomial PDF, and you are going to have 8 trials. The probability on each one is 0.05, and you want exactly 3 for your probability. So you're going to put those in your calculator, and that's the chance of getting exactly 3. Notice that's not going to happen very often. Notice this is much less than 0.05, which is where our cutoff to say this is unlikely, and this is very unlikely. Now, to wrap it up, we need the mean, variance, and standard deviation. Let's keep these in mind. Start with the easiest one, the mean for, remember, we're talking about a binomial distribution or a binomial experiment. The mean, you just multiply n times p. We've used n and p before with binomial PDF and CDF. Just multiply these two together and you get the mean. What you want to do though is you want to write this in your notes, sort of like what some people call a cheat sheet, because occasionally there do get to be several different formulas that you want to be able to use. So for a binomial distribution, you want to keep this on your short list of things to check or to use. How about the variance? Okay, the variance, not hard at all. N times P times Q. What, you know what N is? That's number of trials. P is the probability of success. This is the probability of failure, which you can easily find as 1 minus P. Multiply those 3 together, you get the variance. However, most people don't use the variance very often, so take the square root of that and you'll have your standard deviation. Just remember, when you're getting the standard deviation, remember, don't just multiply those 3, you also have to take the square root for the binomial distribution. All right, let's give this a try. In Pittsburgh, Pennsylvania, I've been there. Have any of you been there? So, what do we have here? We have 56% is our probability. We'll change that to a decimal so we can use it easier. We want the mean, the variance, and the standard deviation. So the mean is n times p, and we're talking about the month of June, and the last day of June is the 30th, so we'll have 30 days times the probability, which is 0.56, and that will give us our mean. And let's see. Oops. Okay, that's the mean. I'll give us the mean. And for variance, we'll take n times p times q. So to get the variance, we'll multiply the 30 days times the 0.56, and q is 1 minus p, so it'll be 0.44, and that'll give you the variance. We also want the standard deviation. So to get the standard deviation, short answer would be take the variance and take the square root. Or, in this case, we'll take 30 times 0.56 plus 0.44 and get the square root of that product. Those are the three numbers we need. There's the mean, 16.8 days. In other words, in June in Pittsburgh, Pennsylvania, according to these results, we'll usually get around 16.8 days of rain in Pittsburgh, Pennsylvania during June. The variance, just multiply n times p times q, or about 7.4. Now, this isn't 7.4 days. 7.4, oh, there isn't. Technically, it would be days squared. What is days squared? Isn't it anything, right? That's why this is rarely used. Instead, oops, the standard deviation, take the square root of it, and the standard deviation is 2.7 days. Days make sense. That means if we're thinking about doing something in next June, that we can expect, if we're in Pittsburgh, Pennsylvania, there might be about almost 17 days of rain, but that could be sort of plus or minus 2.7 days, so that would give us an idea of about 68% of the Junes will have that interval of possible days of rain. So there are our results. On average, 16.8 cloudy days during the month of June in Pittsburgh, Pennsylvania, with a standard deviation of 2.7. And what does that mean? If you had 11 cloudy days or less, it'd be unusual. If you had more than 23, it would also be unusual. And that's it, folks. I think I mentioned rainy days. Actually, we're talking about cloudy days. My apologies. I was rushing through it. Well, that's it. I hope you enjoyed this, talking about binomial things. That's nice when you've got just two options that are possible. You've got a binomial situation. The probability does not change from trial to trial, and so forth. So make sure you make some good notes about what makes a binomial distribution, and also what are the conditions, along with the formulas. Well, you take care of yourself. Keep smiling until I see you next time. Bye.